Good day, DP Labs channel. My name is Kirill, and today we're discussing the production of control arms. In front of you are the parts we use to make them, that is, the blanks. They arrive to us as sheet aluminum, cut by laser, often with small burrs left behind. Next, we carefully clean the surface and remove the scale, ensuring that all the grooves remain even so we can properly fit the mating parts. Then, the part is treated with sandpaper. The burrs are removed and the grooves are cleared. The surfaces that will be inside are sanded to their final state, and then the part is closed up. The outer surfaces are not polished to perfection. They will be finished later together with the welding. These are the tenon and groove parts, and here are the mating pieces. They are installed into these grooves accordingly. The architecture of the inner lever can be seen right here. That is, the only thing missing here is the top plate. Everything else is assembled, the base plates, the load-bearing block that holds the ball joint. Bushings for the silent blocks are welded on here. From this surface to the top of the tenon, we have a 1.5 millimeter recess. This is to allow for welding, so in a way we get a kind of welded rivet. The part is placed on the welding table, the mating piece is taken and installed on top. Next, everything is clamped with clamps. After pressure is applied to the plate, a thin screwdriver or a small hammer is used to adjust all the parts so that they are perfectly vertical, and then the part is tightened down. Once everything is clamped and the assembly is in its proper position, we can start welding. The welding is done in exactly the same way on the table while clamped in place. That is, it is tack welded so that nothing shifts out of place. Well, basically it's not very important. We compared it with and without clamps. Basically, everything stays in its place. The tenons essentially bear all the load, while the weld simply serves to hold the tenons in place. You can clearly see on this already welded lever what the weld looks like. This is before finishing. Accordingly, the welds are still here. Even when they are ground down, we still have 1.5 millimeters of weld left inside, so it all fuses together into one piece. The bushings haven't been welded on here yet. There were a lot of questions in the first video about strength, about aluminum, steel, which tube is best, lack of technology, and other such questions. Well, it's hard to judge whether it's not technologically advanced because we don't have a pipe bender at the moment, but we do have a laser. That's why we do it this way, you see? We don't need any jigs, so this reduces the amount of basic equipment needed to manufacture the ATV. Accordingly, everything is welded on a welding table and requires a welding machine and skilled hands. So the question of technological advancement is still open for us. Perhaps in the future we'll switch to other methods, since we still don't know our production volumes. That's why we're using the method that's currently the simplest for us, one that allows us to quickly change the configuration. And at the same time, we don't have to buy anything extra or invest a lot of money into this process. 10 cents. I'm quitting. I'm going to open my very own brand new hotel. Right now I'm holding a sturdy lever in my hands, which, as you know, we've already tested a little bit. We didn't conduct the tests properly. You could say they were more like welding tests. So what was the testing method? We placed the part under the press like this. We pressed down here first of all because we wanted to see if the bushings would tear off, since that's one of the weak points. The lever doesn't really handle such loads, it works a bit differently. But still, we just bluntly pressed down here. The ears bent, and here one weld cracked, the one that was simply ground down. But there was no reinforcement here, no chamfer, so the weld cracked. But that's normal. As you can see, all the other welds stretched evenly, meaning the part bent as a single hole. Accordingly, after this test, well, here a little less than a ton was applied. They bent. But that's a normal situation, since the lever is fixed, and accordingly, the ears that hold the link blocks take on and hold this load, so it doesn't bend here. Plus, this particular lever is an old version, and it's not correct. In the new version, as you can see, this distance has already been significantly reduced. Accordingly, it can now withstand a significantly greater load right here, and overall the lever has become noticeably smaller. It's more rigid, more compact, and more solid than before. After conducting these tests, we placed the lever on two supports. One support was positioned here, while the other was located here, and we simply pressed it down with a press. Again, this was just for testing the strength of the weld. We needed to understand exactly how it would fail under pressure. As a result, it bent smoothly. There were no tears, as many people wrote, saying it would crack, break apart, or fall to pieces. No, that's not how it works at all. This is AMG3. It's a fairly ductile material, meaning it bends predictably and smoothly without any sudden breaks or failures. Here we had a break almost immediately, but again for the same reason. The weld had been ground down here and there was no bevel, so that's why the break occurred. Next, this particular break along the metal itself only happened under a load of 5 tons. And after 5 tons, it also started to bend smoothly. That is, the part began to fail. So that's quite a significant load. Here as well, the studs didn't get pulled out, so there's nothing to worry about in that regard. It's a pretty sturdy thing. It's not very heavy, and the new ones, which are smaller in size, actually turned out to be much more robust and more durable. In the future, we'll also build a test stand. The main load we need to check is that an axle will be fixed here, a ball joint simulation will be installed here, and pressure will be applied to it. In other words, it will be a pulling load that simulates, for example, a wheel hitting a curb or other obstacles. The control arm will be welded on and finished, and a channel bar will be installed here to which the shock absorber will be attached. For now, we're still considering this part. It's not the final version either. Specifically, these mounts might end up being smaller or more localized. Basically, we don't fully understand the shock absorber's position yet, so we're doing it this way for now. Why don't we design everything, work out the entire architecture on the computer, and make many things out of plywood or create test versions of the control arms? For some people, it's easier to do it on the computer. Some people perceive things better visually. Since I'm the only person working on the development, you see me here, I do it in a way that works for me. It's easier for me to make something, look at it, move it around, and that way I understand it better. That's why I use this method. If someone finds it easier to do everything in models, let them make models. We're not doing it this way because we can't model, it's just more convenient in this particular case. Plus, at the stage when you saw the video with the wooden control arms, that was right after we bought the new gearboxes. And at that very moment we were installing them and checking how everything would fit together. We made, cut, and assembled everything in one day, and it answered a lot of questions. After that, the gearboxes went for scanning, and the control arms went into metal fabrication.